ExCyTIn Bench, evaluating LLM agents on cyber threat investigation.
Okay, so here's our path. We'll start with the core challenge in cyber investigation, look at why this new benchmark was needed, and then see how it was built. After that, we'll cover how the agents performed, the acknowledged limitations, and wrap it all up with 5 actionable takeaways.
All right, let's start with the problem space. We know cyber attacks are getting more complex, more frequent. So what's the real bottleneck for security teams trying to keep up? Well, the scale is a major issue. Just look at cloud environments. Intrusions went up 75% in the single year between 2022 and 2023. That's a huge jump. So with that kind of volume, how does a human analyst even begin to connect the dots?
Right. One of the key tools they use is something called a threat investigation graph. It's essentially a map that connects all the different pieces, the alerts, the events, the indicators of compromise. It helps them visualize the entire attack chain.
Okay, so the scale clearly calls for some kind of automation, and LLM agents are the obvious candidates. But that raises a critical question. How do we actually test if an agent is good at investigating, not just good at reciting facts it has memorized? That's exactly the gap this paper addresses. Most prior benchmarks are effectively knowledge tests. Can the model extract information? This one is different. It's built to measure practical investigation and reasoning skills within a live interactive setting. So building a realistic, interactive testbed for security investigations sounds pretty complex. What did that process actually involve? It broke down into 3 main phases. First, they had to get the right data. Second, they needed to generate the investigation questions. And third, they had to construct the interactive environment itself. For the data, they started with a simulated Microsoft Azure environment. The dataset is pretty rich. It covers 8 different multistage attacks, pulls from 57 different log tables in Microsoft Sentinel, and captures a continuous 44-day period of activity. So it's designed to be realistic. Okay, realistic data is one thing, but how do you generate thousands of valid investigation questions that have verifiable ground truth answers?
They developed a novel approach for that. They built these bipartite graphs connecting alerts to entities, like users or IP addresses. Then they had an LLM trace paths through these graphs to automatically generate questions that are guaranteed to have a correct answer within the dataset.
And the final piece was the environment itself. It's an interactive MySQL database. So for an agent to find an answer, it has to act like an analyst, formulate a SQL query, execute it, get the results back, and then decide on the next step. It's a true interactive loop. All right, so the stage is set. It's a tough, realistic benchmark. How did today's LLMs actually do when they were put to the test?
Well, the main takeaway is that this is a very hard task for all the models they tested. You can see the average rewards scores here for a number of different agents, both proprietary and open source. Nobody is acing this test.
To put a number on it, the best score came from OFAR Mini, and even it only managed an average reward of 0.368. So on a scale of 0 to 1, the top performer isn't even halfway there. It shows there's a lot of room for improvement.
Okay, so performance is one axis. What about cost? Is the best performing model also the most expensive to run?
There's definitely a trade-off. Some models, like Gemini 2.5 Flash and Llama 4M, really stand out on the efficiency front. They deliver pretty decent reward scores for a much lower cost per query.
These are just the baseline scores. Did they test whether different agent strategies or prompting techniques could boost performance? They did, and it turns out the strategy matters quite a bit. Using a method like React, which involves step-by-step reasoning, provided a solid boost. But adding a reflection step, where the agent self-critiques its failed attempts and tries again, pushed the scores even higher. The combination was the most effective.
This is a solid piece of work, but every benchmark has its limits. What do the authors themselves point out as the main limitations here, and what do they see as the next steps?
They called out a few key things. First, it's all based on a single simulated Azure tenant, so it might not generalize perfectly. It only covers 8 specific attack scenarios. The only way for an agent to interact is through SQL queries. And finally, the scoring is either automated string matching or another LLM, which has its own potential biases. As for what's next, I see a few clear paths. One is to use this benchmark to actually train better open source security agents. The environment is also set up perfectly for reinforcement learning because it provides these detailed step-by-step rewards. You could even use the underlying graph structure to explore different ways of teaching an agent. So, if we were to boil this all down for a security AI practitioner or researcher, what are the most important actionable takeaways? There are 5 key ones. First, test agents on their ability to investigate, not just what they know. Second, graph-based approaches are a really effective way to generate structured test questions. Third, advanced prompting, like React with reflection, makes a real difference. Fourth, always look at the trade-off between performance and cost. And fifth, this kind of environment, with its step-by-step rewards, is a great setup for training agents using reinforcement learning.
Ultimately, this benchmark gives us a much clearer picture of where LLM agents stand today. They show promise, but there's a long way to go. And it leaves us with a big question. As these agents get better and better at reasoning, what does that mean for the role of the human security analyst? How will that partnership evolve?